Electromagnetism. In our previous chapter of electricity, you have learned about the heating effect of electric current. We may use many electronic devices works under the principle of magnetic effects of electric current, of heating effect of electric current, such as electric motors, electric generators, electric heaters, etc. How do they work? How do electromagnets work? Is there any relation between electricity and magnetism? Do we produce magnetism from electricity? And how many devices works under the principle of magnetic effects of electric current? Electromagnetism is a branch of physics. The name itself tells the meaning. Whenever a current is flowing through a conductor, a magnetic field is developed around that current carrying conduction. The magnetic field is developed because of passing of current is called as electromagnetism. Hans Christian Ørsted, 1777 to 1851. Hans Christian Ørsted was one of the leading scientists of the 19th century, played a crucial role in understanding electromagnetism. Ørsted carried out an experiment that was never performed before. He placed a compass needle underneath a wire and then turned on electric current. The needle of compass showed deflected. Through this observation, he showed that electricity and magnetism were related phenomena. The unit of magnetic field strength is named the Ørsted in his honor. Ørsted experiment. Take a thermocol sheet and fix two thin wooden sticks of height 1 centimeter, which have small slit at the top of their ends. Arrange a copper wire of 24 gauge so that it passes through these slits and make a circuit. The circuit consists of a 3 or a 9-volt battery, key and copper wire, which are connected in series as shown in figure. Now keep a magnetic compass below the wire. Bring a bar magnet close to the compass. The needle in the compass deflects. This deflection is due to magnetic field produced by bar magnet. When we remove the bar magnet and switch on the circuit, now we observe the position of compass needle. The compass needle deflects. This deflection is due to the magnetic field produced by current carrying wire. Magnetic field. We use term field when a force gets applied on an object by another object without there being any physical contact between them. You have observed this already in activity. Let us call this field, which is responsible for deflection of the compass needle, as magnetic field. How was this field produced? Can we observe the field of a bar magnet? Let us try. Activity. Take a sheet of white paper and place it on the horizontal table. Place a bar magnet in the middle of the sheet. Place a magnetic compass near the magnet. It settles to a certain direction. Use a pencil and put dots on the sheet on either sides of the needle. Remove the compass. Draw a small line segment connected to two dots. Draw an arrow on it from south pole of the needle to north pole of the needle. Repeat the same by placing the compass needle at various positions on the paper. The compass needle settles in different directions at different positions. This shows that the direction of magnetic field due to a bar magnet varies from place to place. Now take the compass needle to places far away from magnet on the sheet and observe the orientation of the compass needle in each case. The compass needle shows almost the same direction among north and south at places far from the magnet. This shows that the strength of the field varies the distance from the bar magnet. Now hold the compass a little above and at the top of the bar magnet. We observe the deflection in compass needle. Hence, we can say that the magnetic field is three-dimensional. That is, magnetic field surrounds its source. From the above activities, we can generalize that a magnetic field exists in the region surrounding a bar magnet and is characterized by strength and direction. Activity: take a cardboard, fix the white paper on the board, place a bar magnet on the middle of the paper. Put two dots on either sides of the compass needle. Take it out. Draw a line connecting the dots which shows the north and south of the earth. Now place a bar magnet on the line drawn in such a way its north pole points towards the geographical north. Now place the compass at north pole of the bar magnet. Put a dot at the north pole of the compass needle. Now remove the compass and place it at the dot. It will point in other direction. Again, put a dot at the north pole of the compass needle. Repeat the process till you reach the south pole of the bar magnet. Connect the dots from N of the bar magnet to S of the bar magnet. You will get a curved line. Now select another point from the north pole of the bar magnet. Repeat the process for many points taken near the north pole. You will get different curves as shown in the figure. These lines are called magnetic field lines. They are imaginary lines. So, these curved lines represent the field lines. If you place a compass at any point on the line, the needle comes to rest along the tangent to the line. So, we conclude that the tangent drawn to the field line at a point gives the direction of the field. Are these field lines closed or open loops? The magnetic field lines appear to be closed loop, but we cannot conclude that lines are closed or open loops by looking at the picture of the field lines, because the alignment of lines that are passing the bar magnet should be considered. If we observe the field lines by a solenoid is the electromagnetical device made up of coil which produces a magnetic field when electric current is passed through it. The field lines outside the solenoid are continuous with those inside. Outside the solenoid, the direction of the field line is from north to south, while inside, the direction is from south to north. Thus, the magnetic field lines are closed loops. If the field lines are grounded, that is, near the poles of a bar magnet, then the field is strong. If the field lines are spread apart, that is, at long distances from the bar magnet, then the field is weak. The field is said to be non-uniform when any one of the characteristics of field, that is, strength of direction, changes from point to point. The field is said to be uniform if both strength and direction are constant throughout the field. Let us define the strength of a uniform magnetic field. Magnetic flux density, that is MFD. Imagine a plane of certain area A placed perpendicular to the field at a certain point in the magnetic field as shown in the figure. A few field lines pass through this plane gives an estimation of strength of the field at that point, and the plane of area A perpendicular to the field is called magnetic flux. It is denoted by pi. Magnetic flux represents the number of lines passing through the imagined plane in the field. Flux depends on the orientation of field is easily defined using the idea of flux. The SI unit of magnetic flux is Weber. The flux through this area gives the strength of the field. This strength of the field is technically called magnetic flux density or magnetic field induction. The flux through unit area perpendicular to field is equal to pi by A. The ratio of magnetic flux through unit area gives the magnetic flux density equals to m into F by area. P equals to pi by A, which implies pi equals to PA units of magnetic flux density is Web by m to the power of 1. It is also called Tesla. Can we generalize the formula of flux for any orientation of the plane taken in a field? Let pi be the angle between magnetic flux P and normal to the plane with area as shown. When the component of effective area of the plane perpendicular to the field is a cos theta, B equals to magnetic flux by effective area. P equals to pi by A cos theta, which implies pi equals to BA cos theta. What is magnetic flux through the plane taken parallel to field? What is the purpose of introducing the ideas of magnetic flux and magnetic flux density? Are there any sources of field other than magnets? Magnetic field due to currents. In activity, we observe that the compass needle is deflected when the current flows through the circuit. From this observation, we conclude that current carrying wire produces magnetic field. Let us discuss about the magnetic field produced by a current carrying wire. Magnetic field due to current in a straight line carrying current. Take a wooden plank and make a hole as shown in figure. Place this plank on the table. Now place a retort stand on the plank as shown in figure. Pass a 24 gauge copper wire through hole of the plank and rub knob of the retort stand in such a way that the wire be arranged in a vertical position and not touch the stand. Connect the two ends of the wire to a battery via switch. Place 6 to 10 compass needles in a circular path around the pole so that its center coincides with the hole. Use 3 or 9-volt battery in the circuit. Switch on current flows through the wire. We notice that they are directed as tangents to the circle. The magnetic field around the wire is circular line in shape. The magnetic field lines due to straight wire carrying the current is shown in figures. This can be verified by sprinkling iron fillings around the wire when current flows in the wire. The direction of the magnetic field around the current carrying wire can be determined by right-hand thumb rule, that is, grab the current carrying wire with your right hand in such a way that thumb is in the direction of current. Then the curled fingers show the direction of magnetic field as shown in the figure. Magnetic field due to a circular coil. Take a thin wooden plank covered with a white paper and make 2 holes in its surface as shown in the figure. Pass insulated copper wire through the holes and wind the wire 4 to 5 times through hole such that it looks like a coil. The ends of the wire are connected to terminals of the battery through a switch. Now switch on the circuit. Place a compass needle on the plank at center of the coil. Put dots on either side of the compass needle. Again, put compass at one of the dots. Put other dot further. Do the same till you reach the edge of the plank. Now, repeat for the other side of the coil from the center. Then, draw a line joining the dots. We will get a field line of the circular coil. Do the same for the other points taken in between the hole. Draw corresponding lines. We will get field line of the circular coil. The direction in which the compass needle comes to rest indicates the direction of the field due to the coil. Thus, the direction of the field is perpendicular to the plane of the coil. Why does the compass needle point in the direction of the field? The north pole of the compass needle is attracted towards the south pole of the magnetic field created by the circular loop. Due to this north pole points towards the south pole of the magnetic field when the current in the coil is in anti-clockwise direction. Direction of magnetic field due to coil points towards you. When the current in the coil is in anti-clockwise direction, the direction of magnetic field due to coil points away from you. The direction of the field due to coil or solenoid is determined with the help of a right-hand rule which states that when you curl your right-hand fingers in the direction of current, thumb gives the direction of magnetic field. Magnetic field due to solenoid. A conducting wire is wound in the form of cylindrical or whose diameter is less in compared to the length is called solenoid. It looks like a helical spring. Take a wooden plank covered with a white paper. Make equidistant holes in its surface as shown in the figure. Pass copper wire through the holes. This forms a coil. Join the ends of the coil to a battery through a switch. Switch on the circuit. Current passes through the coil. Now, sprinkle iron fillings on the surface of the plank around the coil. Give a small jerk to it. An orderly pattern of iron fillings is seen on the paper. The long coil is called solenoid. The field of solenoid is shown in the figure. The magnetic field lines set up by solenoid resemble those of a bar magnet, indicating that a solenoid behaves like a bar magnet. The direction of the field due to solenoid is determined by using right-hand rule. The direction of field due to solenoid is determined with the help of the right-hand rule. The two ends of solenoid behave like south-north poles. The direction of the magnetic field outside the solenoid is from north-south and inside the solenoid is south-north. These magnetic field lines are closed loops. We are saying that a current carrying wire produces a magnetic field. So, the electric charges in motion produce magnetic field. What happens when a current carrying wire is kept in a magnetic field? Let us see. Activity. Stand near the TV screen. Switch on the TV. Do you feel any sensation on your skin? What could be the reason for that? Take a bar magnet and bring it near the TV screen. What do you observe? You can observe that the picture on the screen is destroyed. Why does the picture get destroyed? Is the motion of electrons reaching the screen affected by the magnetic field of the bar magnet? Move the bar magnet away from the screen. Now you will get a clear picture. Repeat this to confirm that the motion of electrons is affected by the field produced by the bar magnet. This must be due to the fact that the magnetic field exerts a force on the moving charges. This force is called magnetic force. Can we calculate the force experienced by a charge moving in a magnetic field? Let a charge Q move with a velocity v perpendicular to the magnetic field B as shown. The value of magnetic force on the moving charge can be found experimentally, and it is given by F equals to QVB. Magnetic force on the charge is the product of three quantities: charge, speed, and magnetic flux density. The equation for magnetic force acting on a charge Q is F equals to QVB and holds well only when the direction of velocity of charged particles V is perpendicular to the direction of the magnetic field B. We can generalize the equation for magnetic force on charge when there is an angle theta between the directions of field B and velocity V. It is experimentally proved that when there is an angle between direction of field and velocity, the magnetic force experiences by the charge is given by F equals to QVB sin theta. What is the magnetic force on the charge moving parallel to a magnetic field? When charge moves parallel to the magnetic field, that is, along the magnetic field or against the field, the value of theta becomes 0. In the above equation, theta is 0 degrees, so that sin theta equals to 0. Thus, the charge experiences no force when it is moving parallel to the magnetic field, that is, along field direction or against field direction. What is the direction of magnetic force acting on a moving charge? Keep your right hand fingers along the direction of velocity of moving charge, and next curl your fingers toward the direction of magnetic field when the thumb gives the direction of magnetic force as shown. This rule is applied for any case of angle between direction of velocity and field. the direction of magnetic force is always perpendicular to the direction of both velocity and magnetic field. The rule is applicable to positive charge. This law states that if the forefinger points towards the direction of velocity of charge or current, middle finger points to the direction of field P, then thumb gives direction of force when the three fingers are stretched in such a way that they are perpendicular to each other as shown. What is the direction of force acting on a negative charge moving in a field? First, find the direction of force acting on a positive charge. Next, reverse its direction. This new direction is the direction of force acting on the negative charge. Let us see an example of force acting on a charged particle. Example: a charged particle Q is moving with a speed v perpendicular to the magnetic field of induction P. Find the radius of the path and time period of the particle. Solution: let us assume that the field is directed into the page as shown in figure. Then the force experienced by the particle is F equals to QVB. We know that this force is always directed perpendicular to velocity. Hence, the particle moves along a circular path and the magnetic force on the charged particles acts like a centripetal force. Let R be the radius of the circular path. We know that centripetal force equals to mv square by r. QVB equals to mv square by r. Solving the equation, we get r equals to mv by bq. Time period of the particle, t equals to 2 pi r by v. Substituting r in above equation, we get t equals to 2 pi m by bq. What happens when a current carrying wire is placed in a magnetic field? Electric current charges in motion. We know that each change experiences a magnetic force. Thus, the current carrying wire, that is, constituting collection of charges in motion, experiences magnetic force when it is kept in a magnetic field. Can you determine the magnetic force on a current wire which is placed along a magnetic field? From the figure, a straight wire carrying current which is kept perpendicular to a uniform magnetic field. This B is directed into the page. Let the field be confined to the length L. We know that the electric current means charges in motion. Hence, they move with a certain velocity called drift velocity. That is V. The magnetic force on a single charge is given by F0 equals to QVP. Let total charge inside the magnetic lead be Q. So, magnetic force on the current carrying wire is given by F equals to QVB. Let this be equation 1. The time taken by the charge Q to cross the field P, T equals to L by V, which implies V equals to L by T. Let this be equation 2. Substituting this in equation 1, we get F equals to Q into L by T into V, which implies F equals to Q by T into LB. Let this be equation 3. We know that Q is equal to the electric current in the wire. I equals to Q by T. Substituting I in the equation 3, we get, which implies F equals to I, L, B. Let this be equation 4. Note, this equation holds well only when the direction of electric current is perpendicular to magnetic field. What is the force on the wire if its length makes an angle 0 with the magnetic field? Let 0 be the angle between direction of current and magnetic field. Then, the force acting on the current carrying wire is given by F equals to I, L, B sine 0. That is, at any angle. Let this be equation 5. How could you find its direction? You can use right-hand rule to find out the direction of force on the current carrying wire. Let us see the results of force applied on a current carrying wire by an experiment. Activity: take a wooden plank, fix 2 long wooden sticks on it. These sticks are split at their top ends. A copper wire is passed through the splits. Ends of wire are connected to a battery of 3V through a switch. Close the switch to make the circuit. Current passes through the wire. Now, bring a horseshoe magnet near the copper wire as shown in the figure. Observe the deflection of the wire. Change polarities of the horseshoe magnet. Again, observe the deflection. Repeat this by changing the direction of current in the circuit. When current passes through wire, it produces a magnetic field and its field overlaps with the field by horseshoe magnet and gives a non-uniform field. The field in between north and south pole of horseshoe magnet is shown in the figure. Let us imagine a wire passing perpendicular to the paper. Let the current pass through it. It produces magnetic field as shown in the figure. The resultant field will be as shown below. We can see that the direction of the field lines due to wire in upper part coincides with the direction of field lines of horseshoe magnet. The direction of field lines by wire in lower part is opposite to the direction of the field lines of horseshoe magnet, so that the net field in upper part is strong and in lower part is weak. Hence, a non-uniform field is created around the wire shown in figure. Therefore, the wire tries to move to the weaker field region. Consider a rectangular coil kept in uniform magnetic field as shown in the figure. Switch on the circuit so that the current flows through the coil. The direction of current is shown in the figure. The sides AB and CD of the coil are always at right angles to the magnetic field. According to right-hand rule, at AB the magnetic force acts inward perpendicular to the field of magnet, and on CD it acts outwards. The top view of coil is shown in the figure. The force on the sides BC and DA varies because they make different angles at different positions of the coil in the field. At BC, magnetic force pulls the coil up, and at DA, magnetic force pulls it down. The net force acting on AB and on CD is 0 because they carry equal current in the opposite direction. Similarly, the sum of the forces on sides BC and DA is also 0. So, net force is 0 on the coil. But the rectangular coil comes into rotation in clockwise direction because equal and opposite pair of force acting on the two sides of the coil. If the direction of current in the coil is unchanged, it rotates up to half rotation in one direction and the next half in the direction opposite to previous, like to the flow motion. If the direction of current in the coil is changed, the coil will rotate continuously in one and the same direction. To achieve this, brushes B1 and B2 are used, as shown in the figure. These brushes are connected to slip rings C1 and C2, which rotate along with the coil. Initially, C1 is in contact with B1 and C2 is in contact with B2. After half rotation, the brushes come into contact with the other slip rings in such a way that the direction of current through the coil is reversed. This happens every half rotation. Thus, the direction of rotation of the coil remains the same. This is the principle used in electric motors. In electric motors, electrical energy is converted into magnetical energy. We have learned that a current-carrying coil rotates when it is kept in a uniform magnetic field. What happens when a coil without current is made to rotate in the magnetic field? How is current produced? Electromagnetic induction, Faraday's law. Take a wooden base as shown in figure. Fix a soft iron cylinder on the wooden base vertically. Wind copper wire around the soft iron as shown in figure. Rotates a metal ring which is slightly greater in radius than the radius of the soft iron cylinder and inserts it through the soft iron cylinder on the wooden base. Connect the ends of the coil to an AC source and switch on the current. The ring is elevated, that is, raised in the air. On the coil, switch off the current. The ring will jump into the air very dramatically. Remove the AC supply and connect a DC supply. Observe what happens. Could the ring be elevated if DC is used? The metal ring elevates when AC is used. Therefore, the net force on it should be zero according to Newton's second law. The free body diagram of metal ring is shown in figure. Weight W acts down. To balance it, a force F equal in magnitude and opposite in direction should act as shown in figure. What is this unknown force acting on the metal ring? In this activity, AC is used. AC changes both its direction and magnitude in regular intervals. Due to the magnetic field produced by current in the coil, one end of the coil behaves like North Pole and the other end behaves like South Pole for certain time interval. For the next interval, the coil changes its polarity. Assume that the current flows in clockwise direction in the solenoid as viewed from the top. Then the upper end becomes a south pole. An upward force is applied on the ring only when the upper side of the ring becomes a north pole. It is only possible when there exists anti-clockwise current viewed from the top, that is, in the ring. After certain intervals, solenoid changes its polarity, so that the ring should also change its polarity in the same intervals. This is the reason why the metal ring is elevated. What is responsible for the current in the metal ring? AC is not a constant ring. Due to the change in the current, there is a variation of produced MF takes place. The magnitude of magnetic induction, MI, and direction, MI, changes, but the area of the ring is constant. But the metal field with ring changes. Then magnetic field changes means the number of magnetic lines of force through the area changes. That is, magnetic flux density changes. If DC current is used, the metal ring lifts up the pole down immediately. Why? When the flux linked with the metal is zero, when there is no current passed through the coil, there is no change in the position of metal ring. Whenever a DC current flows through the circuit, then the magnetic flux linked with the circuit changes at this instant. There is a change in flux linked with ring when we switch on the current. Whenever we switch off the power again, there is no charge in the magnetic flux. It falls down. The metal ring lifts up and pulls down. In this case also, there is a charge in the flux linked with the coil. Aim: to understand Faraday's law of induction. Materials required: a coil of copper wire, a bar magnet, galvanometer, etc. Procedure: take a copper wire in the form of a copper. Connect the terminals of a coil sensitive galvanometer as shown in the figure. Normally, we cannot expect any deflection of needle in the galvanometer because there is no electromotive force, that is EMF, in the circuit. Now, if we push a bar magnet towards the coil with its north pole facing the coil, the needle in the galvanometer deflects, showing that a current has been set up in the coil. The galvanometer does not deflect if the magnet is at rest. If the magnet is moved away from the coil, the needle in the galvanometer again deflects, but in the opposite direction, which means that a current is set up in the coil in the opposite direction. If we use the end of south pole of a magnet instead of north pole in the above activity, the deflections are exactly reversed. This activity proves that the change in magnetic flux linked with a closed coil produces current. This experiment proves whenever there is a continuous change of magnetic flux linked with a closed coil, a current is generated in the coil. This is one form of Faraday's law. After observing this, he proposed a law of electromagnetic induction, which is as follows. The induced EMF generated in a closed loop is equal to the rate of change in MF passing through it. In mathematical form, we can write this as induced EMF equals to change in flux by time. Sigma equals to triangle theta by triangle T. Let this be equation 1. The above equation is called Faraday's law of induction is flux, that is pi linked with coil. Let theta 0 is the flux linked with single turn. If there are n turns in the coil, the flux linked with the coil is n pi 0. Pi equals to n pi 0. Let this be equation 2. So far, we have not specified the direction induced EMF or induced current. What is this direction? Can you apply conservation of energy for electromagnetic induction? When we push a magnet towards the coil magnet, current is generated, electromagnetic induction takes place, and then magnetical energy is converted into electrical energy. We know that when a bar magnet is pushed towards a coil with its north pole facing the coil, an induced current is set up in the coil. The north pole of the magnet induces north polarity in the coil. As a result, there will be a repulsive force between coil and magnet. Hence, we need to do work to overcome this force. This work done on the magnet is converted into electrical energy in the coil. As a result, an induced current is produced in anti-clockwise direction with respect to north pole of the bar magnet. In this way, conservation energy takes place in electromagnetic induction. Let us see a case where the bar magnet is pulled away from the coil with north pole facing the coil. In such case, the coil opposes the motion of bar magnet to balance the conversion of mechanical energy into electric energy. This happens only when the north pole of the magnet faces the south pole of the coil. Direction of induced current in the coil in this case. Invertibly, the direction of induced current in the coil must be in anti-clockwise direction. In simple terms, when flux increases through coil opposes the increase in the flux. And when flux decreases through coil, it opposes the decrease in the flux. This is Lenz's law. Lenz's law states that the induced current will appear in such a direction that it opposes the changes in the flux in the coil. When we push a magnet towards the coil magnet, current is generated, electromagnetic induction takes place, and then magnetical energy is converted into electrical energy. We know that when a bar magnet is pushed towards a coil with its north pole facing the coil, an induced current is set up in the coil. The north pole of the magnet induces north polarity in the coil. As a result, there will be a repulsive force between coil and magnet. Hence, we need to do work to overcome this force. This work done on the magnet is converted into electrical energy in the coil. As a result, an induced current is produced in anti-clockwise direction with respect to north pole of the bar magnet. In this way, conservation energy takes place in electromagnetic induction. Let us see a case where the bar magnet is pulled away from the coil with north pole facing the coil. In such case, the coil opposes the motion of bar magnet to balance the conversion of mechanical energy into electric energy. This happens only when the north pole of the magnet faces the south pole of the coil. Direction of induced current in the coil in this case. Invertibly, the direction of induced current in the coil must be in anti-clockwise direction. In simple terms, when flux increases through coil opposes the increase in the flux. And when flux decreases through coil, it opposes the decrease in the flux. This is Lenz's law. Lenz's law states that the induced current will appear in such a direction that it opposes the changes in the flux in the coil. Could we get Faraday's law of induction from conservation of energy? Let us see. Let us arrange an apparatus as shown. It consists of a pair of parallel pair conductors which are spaced I meters apart in uniform magnetic field of B. We can hold another bare conductor in such a way that it is in contact with the two parallel wires. A galvanometer is connected to the ends of parallel conductors to complete an electric circuit. Now, if the cross wire, that is, cross conductor, placed across parallel conductors is moved to the left, galvanometer needle will deflect in one direction. If this cross wire is moved to the right, its needle deflects in a direction opposite to the previous deflection. A current will be set up in the current only when there is an EMF in the circuit. Let this EMF be sigma. According to principle of conservation's energy, this electric energy must come from the work that we have done in moving the cross wire. If we ignore friction, the work done by this applied force equals to Fs, that is, where S is the distance moved by cross conductor. Can you derive an expression for the force applied on cross wire by the field B? We know that it is equal to B from equation 4 of previous discussion, that is, F equals to Pi by S. Let this be equation 8. This force must oppose the applied force. The direction of applied force determines the direction of current through the cross wire. Here we are doing positive work. The work done by us in moving the cross wire converts into electric energy. So the work done is given by W equals to Fs equals to Pi by S. Let this be equation 9. Using equation 8, when we put the cross wire across parallel conductors, it makes a complete electrical circuit which encloses a certain amount of magnetic flux. Now, as we move the cross wire to the left, the area of the loop, that is, formed by the parallel conductors and cross wire, decreases. The flux through the loop also decreases. The decrease in flux is given by triangle pi equals to B by S. Let this be equation 10. Here, B is perpendicular to the area, IS. From equation 9 and 10, W equals to triangle pi into I. Let us divide both sides of this equation by triangle T. W by triangle T equals to I into triangle pi by triangle T. Let this be equation 11. Electric power. P equals to I triangle pi by triangle T. We know that electric power is the product of current and EMF of voltage. Sigma equals to triangle pi by triangle T is obviously equal to induced EMF. Electric power P equals to sigma I. Let this be equation 12. Thus, the electric power generated in the circuit is equal to product of induced EMF and the current. Thus, the mechanical energy utilized to move the cross wire in 1 second is converted into electric power triangle pi by triangle T into I. This is nothing but conservation of energy. Dividing equation 9 by triangle T, we have W by triangle T equals to Fs by triangle T equals to Pi by S by triangle T. Let this be equation 13. Here, S by triangle T gives the speed of the cross wire. Let it be taken as V. Then we get electric power P equals to W by triangle T equals to Fv equals to Pi by V. Let this be equation 14. Power is also given as force times velocity. From equations 12 and 14, we get W by triangle T equals to sigma I. Sigma I equals to Pi by V. We get sigma equals to PIV. This is called motional EMF. The above equation is not Faraday's law of induction because it is not related to the loop. It is useful when a conductor moves in the uniform magnetic field. Let us see a few examples on induced EMF. Example: the magnetic flux inside a coil of 400 turns changes for each single turn with time as shown. Determine the maximum induced EMF generated in the coil. Is there any change in induced EMF from t equals to 0.1 second to 0.3 second? Solution: from the given graph, the increase in magnetic flux through one turn of coil in 0.1 second is 0.001 Wb. According to Faraday's law, the maximum induced EMF generated in the coil is given by sigma equals to N triangle P by triangle T. Substituting the values, we get sigma equals to 400 into 0.001 by 0.1 equals to 4V. From graph, there is no change in magnetic flux through coil from t equals to 0.1 second to 0.3 second. Hence, no EMS is generated. Example: find the length of the conductor which is moving with a speed of 10 m by s in the direction perpendicular to the direction of magnetic field of induction 0.8 t. If it induces an EMF of 8V between the ends of the conductor. Solution: given that V equals to 0.8 t, V equals to 10 meters per second and sigma equals to 8V. Using sigma equals to PIV, 8 equals to 0.8 into I into 10. L into length of the conductor equals to 1 meter. Applications of Faraday's law of electromagnetism or electromagnetic induction. Electromagnetic induction. Electromagnetic induction is all around us. You might have seen that during security check, people are made to walk through a large upright coil. That wire produces a alternating weak MF when you are walking through a coil. If we carry any materials made of iron, then it behaves like a magnet, then MF is developed around it. Then the magnetic flux linked with the coil changes. Then the induced current is generated in coil, triggers on alarms. The tape recorder which we use to listen to songs or record voices works on the principle of the electromagnetic induction. It consists of a piece of plastic tape coated with iron oxide and magnetized more in some parts than in others. When a tape is moved through a small coil of wire, some field is generated. Then magnetic flux produced by a tape changes, which leads to generation of current in small coil of wire. An induction stove works under the principle of EMF. A metal coil is kept below the cooling surface, then it carries AC current. So, magnetic field is produced. When we place a metal on the stove, then The procedure MF enters to the pan by closing the bottom surface of the pan, and EMF is induced in it. Because of induced EMF, induced current passes through the pan because of resistance. Due to this opposing force, some heat is generated. That produces heat is induced to water. That is why we call this stove as induction stove. Have you ever thought from where we get electric energy? Let us learn about it. Electric generator and alternating currents. What happens when a coil is continuously rotated in a uniform magnetic field? Does it help us to generate electric current? Let us see. Consider a rectangular coil. Let it be held between the poles of curve-shaped permanent magnet as shown in figure. As the coil rotates, the magnetic flux passes through the coil changes. According to the law of electromagnetic induction, an induced current is generated in the coil. Is the direction of current induced in the coil constant? Does it change? Consider initially the coil. Positional in such a way that metallic flux passes through it. When the coil is at rest vertical position, with side A of coil at top position and side B at bottom position, no current will be induced in it. In this position, the current in the coil is zero. When the coil is rotated in clockwise direction, current will be induced in it, flows from A to B. During the first quarter of rotation, the current increases from 0 to a maximum and reaches peak value when the coil is in horizontal position. If we continue the rotation of coil, current decreases during second quarter of the rotation and once again becomes 0. When coil comes to vertical position with side B at top and side A at bottom, during second part of the rotation, current generated follows the same pattern as that in the first half, except that the direction of current is reversed. Can you guess the reason for variation of current from 0 to maximum and vice versa during the rotation of coil? Can we make use of this current? If so, how? Let us find out. Electric generator and direct currents. From figure, the ends of the coil are connected to two slip rings and two carbon brushes are arranged in such a way that they press the slip rings to obtain current from the coil. When these brushes are connected to external device like TV, etc., we can make them work with current supplied from ends of carbon brushes. This current is called alternating current, that is AC, in which the direction of charge flow reverses periodically. So, AC possesses certain frequency. The generator that we discussed here is called AC generator. These AC EMF and AC are expressed in terms of RMS values. Let I0 and V0 be the peak values of AC and AC EMF. IRMS equals to I0 by root 2 and VRMS equals to VO by root 2. How can we get DC current using a generator? What changes do we need to make in an AC generator to be converted into a DC generator? Let us find out. Consider a rectangular coil. Let it be held between the poles of curve-shaped permanent magnets, as shown in figure. As the coil rotates, the magnetic flux passing through the coil changes. According to the law of electromagnetic induction, an induced current is generated in the coil. If two half slip rings are connected to ends of the coil, as shown in the figure, the AC generator works as DC generator to produce DC current. Let us see how it works. When the coil is in vertical position, the induced current generated during the first half rotation raises from 0 to maximum and then falls to 0 again. As the coil moves from this position, the ends of the coil go to other slip rings. Hence, during the second half rotation, the current is reversed in the coil itself. The current generated in the second half rotation of the coil is identical with that during the first half of the direct current DC for one revolution. Hence, this current is called direct current, that is DC.